You ask GPT-5 a complex question, and within seconds, it responds like it actually understands you. Yet beneath that clean interface lies an alien geometry that even its own creators do not entirely comprehend. We routinely watch it write functioning software architecture from scratch. We see it analyze dense medical data with precision. But there is no digital person sitting inside the computer. It possesses no conscious mind and holds no actual beliefs. It is a cold, mechanical structure operating on a massive scale. To figure out how a machine constructs such a convincing imitation of a human, we have to abandon our human intuition entirely and look at the exact mathematical engine firing at its absolute core. When you type a prompt, the system does not read it as text. It shatters your words into tiny numerical pieces called tokens. These tokens are the raw fragments of our language. This diagram shows the single mechanical process driving the entire system. Once the machine holds those tokenized fragments, it asks itself one mathematical question over and over again, calculating the exact probability of what the next token should be. To make that single prediction accurate, it relies on hundreds of billions of invisible parameters. These parameters were trained on a massive trove of human data, books, websites, and code, tuning themselves to recognize the invisible structural patterns buried inside our language. When this prediction cycle repeats across trillions of data points, it generates patterns so complex they begin to mirror the logic of the people who wrote the original text. The system derives actual meaning by converting those tokens into exact physical coordinates within a massive multidimensional geometric space. Inside the machine, words are physical locations. This animated 3D map shows how concepts physically cluster together. By mapping vocabulary to geometry, the model discovers that spatial direction equals semantic meaning. If you start at the coordinate for the word king, subtract the concept of man, and add the concept of woman, the math lands precisely on the coordinate for queen. But identical words carry different meanings depending on their context. The word model in machine learning splits its physical trajectory away from the word model on a fashion runway. To solve this ambiguity, the system uses a digital spotlight called the attention mechanism. It instantly weighs the surrounding context, calculating your specific intent based on the words you place near each other. By plotting your words geometrically and using attention to weigh the context, a basic prediction engine can flawlessly decipher highly complex human intent. Older language models were built to spit out the next word as fast as possible. GPT-5 uses a different internal architecture. Instead of racing to the next word, it pauses to map out multi-step problems before it generates a single character. Because it now takes time to calculate these logic steps, we are observing emergent abilities. These are complex behaviors and skills that human engineers never explicitly programmed into the code. It now acts as an autonomous coding agent, capable of building interactive 3D web applications line by line without human intervention. It routinely scores gold medals on competition math tests, cracking logic puzzles that stump top human mathematicians. By granting the system time to mathematically think, it gained the ability to navigate logic gates and solve problems rather than just mimicking the flow of a sentence. An intelligence trained on the unfiltered internet knows how to generate toxic or dangerous material just as easily as it writes helpful code. Imagine an immortal chef who has memorized every cooking technique in history, but has absolutely no idea what humans actually like to eat. To keep it safe, humans step in. Testers evaluate and rank the system's outputs, iteratively teaching the model the invisible boundaries of human preference. This flowchart illustrates how the system enforces those boundaries. Instead of acting like a brick wall that simply refuses to answer, it intercepts dangerous requests and uses what engineers call safe completions. It proactively guides the user to a safe alternative. Through millions of these feedback loops, engineers tame a raw mathematical anomaly into an aligned human collaborator. Following all of that deep reasoning, spatial mapping, and safety checking, the model produces its immediate output, a massive, messy list of raw numerical scores for every single token that could possibly come next. This diagram shows the final step. A mathematical function called the softmax converter activates, translating those messy raw scores into a clear probability distribution. It highlights the single most likely answer. The model selects the brightest path on that list, executes the token, and instantly repeats the entire calculation process. Every profound insight and helpful line of code generated by the AI is ultimately bound to this single repetitive loop of cold probability. The internet changed how we access information. This technology changes how we produce it. The system can now execute 1,000-hour research tasks and discover new science on its own, moving beyond a tool that simply answers queries. Yet despite these monumental capabilities, you are not talking to a conscious mind. You are interacting with a vast prediction system mapping numbers in the dark.